Hey, Luke.
Hey, Jordan.
How are you?
Pretty good.
Ready for the exam on Monday?
I don't know. I'm not really sure what's going to be on it
Yeah,
yet. I'm maybe a little worried, but
yeah. I'm a little worried, but thankfully now that we have a few extra days to work on it,
yeah.
hopefully I'll be ready by then. Just gonna go back through all the lectures and see if I missed any important details.
I think I'm more worried about like conservation stuff than like multiple stuff.
Like for the math methods class, we knew pretty much everything that was gonna be on there.
Yeah.
And I studied for like 4 days straight, just
Yeah.
straight studying. So I felt pretty good about that one. So that was good because I was more worried. So this summer I went through a lot of E&M stuff.
Gotcha.
So I was like, okay, well, I'm feeling a little bit more confident with E&M. I'm going to really focus on math methods. And I did, I got an A on the first E&M exam. And then, so I was like, okay, I'm feeling pretty good about this class. But the first exam, the first exam for math methods, I can't remember what my grade was. Let's see. I think I got like a 78 or something.
Gotcha.
Let's see.
Hello guys.
Hello.
Hi, Shajesh.
Hey. Luke.
Have you graded the exams?
Yes, I did. Did I not post?
Oh, you might have. I just.
Did you guys see your scores? Was it? So no one comes to know about it when I posted. Oh, I know, because I did not release the grade. Because I didn't curve them. Yeah.
Oh, okay.
I was just lazy.
Thank you.
And for midterm exams, I have not totaled it. But I list them, I guess.
Oh yeah, Moses, did my emails go through? Because I didn't see that you had responded, so I didn't know.
Oh, yes, they did. I did not respond.
I was just making sure you saw them because you had asked, so I just wanted. I think they went through.
About the last problem on the midterm?
Yeah.
Yeah, I got those. Yeah, that was helpful. Thank you.
So this is your group.
Yes, our
Yeah.
email thread.
Good. Yeah. I'm glad that's the first time I think, at least at a global scale happening. But
Yes.
good.
Yes,
Yeah, let me just say that the midterm exams were graded. Still, there is a lot of points remaining, so don't give up by any chance. So grades can change significantly. Oh, I didn't post the midterm yet. Sorry, the homework yet. So let's say the next homework is homework 6, I suppose. think this will start writing better. I think it's a new one. So homework 6, let's say 1 week from today. Yeah. Do you think this will start writing?
We can't see anything online. We just see it. It just looks like an eraser. Better. Is this slightly better? Maybe not thick enough. It's way better. Yeah, it's perfect.
Check. Down 3 is on November 5th. And I think November 19th is the last day of classes before Thanksgiving. And after that, there is 1 week more of class. So I think we crossed the halfway mark. Okay. Yeah, we did not meet after midterm. So how was midterm?
I wish it were better. I wasn't as prepared as I could have been.
What about from my side? Was the exam reasonable?
I mean, yeah, the first problem threw me, but everything else was definitely
Yes.
coverage. So.
Yes, first problem, yeah. Yeah, it was a tricky problem, I think.
I got lucky because if you look back through your old exams, it was a question that you had. So I had worked it. So when we got to the problem, I felt pretty good about it. But
Okay, good. Yeah, that explains it because I usually think of those problems as if you get a small hint to it, then you get it done. Otherwise, you're just struggling with it. And so it is not really a measure of anything. But I feel it's a nice problem to give because it always gives you the complex numbers. Is like often you think, oh, this is so trivial. What is there in it? But these are simple. You can make even a small topic hard, right? Just standard. But again, I don't think you should mind or you should judge yourself based on that problem alone. Even though, so that's a 20-minute point problem, but that shouldn't be the judging case. But other problems, make sure you got them right. I think most of the other problems, was reasonable, I suppose. The cross product, I think most of you guys did get it done, but still, or I should say most of you did careless mistakes. I was not very, I think, in an exam, I'm surprised that you guys made, even when I gave the expression, you guys made that mistakes. Almost half of you made mistakes in that. Either you forgot to put an H1 or in the front or in the top or in the bottom row. So
I didn't use the scale factors. I haven't seen my exam, I guess, but
you don't have to. You don't have to use it.
I just used the fact that it was phi hat, and then did the cross product where the other terms were 0. And
no, it seems like you did use. Is yours? I think it is yours. Or maybe it is yours. You did use the formula. At least you write it.
I wrote it on the front page because you put it on the board, but when I got to the problem, I used the phi hat term.
What did you say? I think so. Unless I'm understanding, that's yours, I think. You don't remember your own work.
Maybe.
Yeah, would you agree he used the?
Yeah, I mean,
I mean, I used the scale factor, but I didn't use the exact formula where I did 1 over H1, H2, H3.
you just recalled it from memory?
Yeah, I just, so,
Like you write that down in your first step, but that's okay. Let's not worry about that.
I'll
Yeah.
show you. I'll pull it out.
Or maybe I can show you the camera, right? That's the best. I think you don't remember what you wrote.
Let me see.
Believe that you, okay. Would you agree that this is your work?
Yeah,
So that's the scale factors.
yeah, R squared, but I'm saying that the way that I did it, I feel like I didn't use the same thing you used. I used H1, H3 and H1 or H1 M3 that you put. That's the only term that I used with the 1 over H1, H2, H3 being R squared sine theta.
Maybe you're misinterpreting. It's the same thing.
Okay. Yeah, I
Or
guess
maybe, maybe what you're saying is that usually what I do, that's not what you're using.
that's
I
how
don't-
I'm using the.
This is not typically what I encourage people to do because I don't even use this formula. But maybe that's what you're trying to say. But in the last 3 weeks or so, I've been giving this formula because everyone is much more comfortable with this formula than using the explicit way. Because often if you're not using the curl, then these formulas don't help. That's my point. And often you do in situations where it's not just a curl. But yeah, okay. We'll see when
And did I get the first problem right? I was.
Yes, you're the only one who got the first problem right. So no one else got it. That's a very hard problem to assess because either you get it right or you don't get it right. So it's a bad exam problem in that sense. So I did get, I think a couple of you guys did say right after the exam that it was not a good problem. Yeah. But yeah, happens.
Yeah, I just happened to work it a couple days before the exam because I think you had it either on last the last exam or the exam before that 2 years ago or last year's.
Probably a few years ago. I think first time when I was teaching this, I gave this, I think. So, problem 2, all of you guys, the cube roots of 1, that should be, you should know how to do it if it got that wrong or if you had confusions with it. You should make sure that you got that, you understand that. Problem 3 is conceptual. I can understand that could be problems, but then it was a homework problem. That's why most of you did do it okay. And 4th problem was a curve, which was fine. So, and 5th problem, I graded, I think a couple of you submitted, and it seems like you've been yeah. Okay, so let's do a little more of complex analysis and finish this and do something else afterwards. And this has to do with, this is what is, so we did differentiation of analytic functions. Now we want to do integrals, and integrals has this nice feature that analytic function, if a function is analytic in a domain and you do a contour integral around that in that domain, then it is 0. So let's see. So this is what is called Cauchy theorem, I think. Cauchy's theorem. So let's have a complex plane. And let's have a contour. The contour is basically a path on a plane. That's what it is. And the theorem is that if you were to integrate f of z, and if this was a closed integral along this c, this is equal to 0 if f of z is analytic everywhere inside the contour C, in the domain.
Well, I have one quick question. When you, like online and a lot of like the math books, they use like, once you verify Cauchy's conditions, then they say as long as the function is continuous, then as long as the function is continuous, then it is analytic. Some of them say that instead of you know, using the other steps where you make sure that it's you know, from, if you take the limit from any direction, that you get the same.
Well, that's probably not correct, right? You can think of, you can probably build functions like, so for example, this function is continuous, right? This is a real function, correct? But its derivative when you come from the right hand side and left hand side is not the same, right?
Yeah.
So it's not in the very trivial sense, it's not isotropic. There are only two directions possible.
Mm-hmm.
And it's not an isotropic derivative. So just continuity surely doesn't guarantee you that its derivative exists. So you can probably build such a function on a complex plane.
Maybe I'm not understanding exactly how they do. It's like something within the domain of the, maybe I'm not understanding the terms, the mathematical term.
So the point is that I think this is a challenge with complex or analytic function, is that the sufficient condition is not precisely, it is more conceptual than algebraic. So you have to do it for each problem, I suppose. Do you see, for example, if some function is going to infinity at some point, it might be continuous right at that infinite point, but then you don't account for it because infinity is not allowed. So those kind of caveats are there. Most of the time, as far as user level goes, I would say you don't get affected unless I ask you a question on that. At a user level, what you do is you check for the Cauchy-Riemann conditions, and mostly you just check for whether it goes to infinity or not at that point. And that is what we will call it a pole. It's called a pole of a function. If there is a pole, then you say that, oh, that's not analytic at that point. Now, if you're in a new domain where you're really analyzing a function, then I would say that isotropic derivative, the concept of isotropy, the way you come from each direction and you get the same derivative again and again for every direction, that's the best intuitive way of doing it. Now, there might be cases where it is continuous and it is done, but I don't think there is a universal statement like that, that, oh, if it is continuous, then it's a sufficient condition. I think so, yeah. And I think, for example, at least for continuity, I can give you a counter example, something like that.
Because in this function to me is not continuous because it has a sharp turn. So like,
No,
if
it's
you-
continuous.
So
It is
so
continuous.
it is continuous, but I don't think it would satisfy the Cauchy-Riemann conditions.
Oh, that's also correct. Yeah.
So I thought Jordan was saying that the Cauchy-Riemann conditions together with
yeah,
continuity.
so if it satisfies, so step one is, does it satisfy the Cauchy Riemann conditions? And if it does, then if the function is continuous within the domain of the function, then it is.
It is sufficient condition.
Yeah, that's what I read a lot of. So
How about
I read a lot of math books, and a lot of them use that.
might be okay. I'm not, but I would say okay. For example, what if there is a pole?
Then it wouldn't be continuous because
Yeah.
so if there's a hole, it's not continuous, and if there's a sharp turn, it's not continuous. Only smooth curved functions could be.
I will give that to you if that is okay. It's just that I mean, yeah, I do know that. Yeah, okay. How about that? I usually go with isotropic derivative. That's what I do. It seems to me more reasonable, but then, yeah, let me say I don't know. I'm not sure that, like, it's always the case, right? What if there is one case? Then what will be needed here is that I will have to start with continuity and Cauchy-Riemann and prove that it is analytic. And maybe there is a proof like that. Yeah. I'm not aware of that. Yeah.
Okay.
Like there must be. Yeah, if they are writing it, there must be. Yeah. Okay. So let me leave that open. Yeah, instead of me contradicting it, that might be better.
Can I say one last thing?
Yes.
So I've seen it as like if Cauchy-Riemann conditions are satisfied and there's like some level of continuity in the partial derivatives. So I don't know. I don't know if that's the same condition.
Do you have to check all the partials, or do you?
I don't know.
Or if you check one, is it sufficient? Because if it satisfies, then.
I
Right.
think log of z might be another example. Like logarithm of z, that is not continuous, right? It has a whole line of discontinuity there. Is it analytic or not? Right. That's what you could explore, right? So, so ask the question if the logarithm of a function z, just f of z, right? So f of z is equal to log of z, and we will see this again. This has a discontinuity on a branch line. So if you can choose this wherever you want, but starting from point 0 all the way to infinity, there is a discontinuity there. And then you can ask, is it analytic or not? So that's a way you want to look at it. All right. So maybe example wise one can look for. So yeah. So maybe I'm being very safe here. I don't want to make a very generic statement that it is continuous. I'm not completely convinced. But if someone is writing that must be. If you are saying that 5 textbooks write this, then it must be correct. Okay. So I have been just using.
There were several resources I saw that said that.
Tell that again.
There were several resources I saw that said that, but you know how some of those are, it's like they only give you a piece of the information that they expect you to know, and then later on they tell you like, hey, well, we told you this, it's not necessarily true. That's why I wasn't sure. Because I think a lot of interesting details come whenever you know something satisfies the Cauchy-Riemann, and then you can see if it's a
how about this? Let me explore this. Okay, let me think about it. So you guys are saying that if it is Cauchy-Riemann conditions are satisfied, and if it is continuous, right? And by continuous, I mean it's smooth in all directions, right? Then it is satisfied. Let me look into it. Yeah, basically, I just have to think of a counter example maybe. And you said smoothly continuous, or it could be, oh,
So
then it won't. You said if it is not smoothly continuous, then Cauchy
I
Riemann will
just
not.
remember from my Calculus 1 course when we were doing limits, the general idea was that, you know,
No, that surely doesn't work. No, that surely doesn't work. If you're going by that,
I'm just saying
intuition-
for a sharp turn for on a graph, it could not be continuous. A function that has, you know, points, like sharp points,
it is continuous. In one dimension, it is continuous.
it is continuous.
I think what Luke is trying to say is that on a complex plane, it won't satisfy Cauchy Riemann conditions probably. I'm not sure, but that's his point. If you have a sharp kink, then
It couldn't satisfy, right?
so I don't know that. Yeah. Yeah. So let me leave that open. Like it doesn't change anything that I said. It's just that I'm doing the blunt way, and you are interested in a global statement. Right? I'm trying not to say that. Yeah. Just being safe. That's all. It might be correct. Like again, if there are 5 textbooks saying that, usually they are right. They don't write wrong things. Yeah. So let me think about it. Reasonable?
Yes. Sorry for the.
Yeah. So
It was just.
again, when we are doing this integral theorem also, again, there will be cases where you might be able to analyze it. So this is another way of analyzing that. Yeah. Like that's one function you can think of. Another is, let's say, square root of z. Right? That has problems. Square root of z is not analytic everywhere. So, so you want to analyze those kind of simple examples and see. Okay.
Well, square root of z wouldn't satisfy the Cauchy-Riemann conditions either, then would it? Because it's kind of there's a dependence on the conjugate. Because if you put the square root in the denominator, it's you're
this should satisfy Cauchy Riemann at most of the places. Yeah. Again, yeah, of course, if it's, I don't know, yeah, I have to think about it. Because this is very much like log of z. Like these are, like you say, either you have a pole or a branch cut, so these are branch cuts on it. And like branch cut is basically a discontinuity. So, again, this will have a discontinuity at this along a line. So we'll see this. How about this? As we proceed, keep asking this question. I'm not disagreeing, but I'm not trying to agree completely just because I want to be careful.
okay.
Right. That is all I'm trying to say. Yeah. Okay. So if I proceed, good questions though. Yeah. Make me think. Okay. So we did last time very much statement like Stokes' theorem. We tried to derive. We pretty much did Stokes' theorem on a complex plane. If you have derived Stokes' theorem before in any vector calculus class, we pretty much did that. And what we concluded is that if a function is analytic, then you have this to be 0, and that's what is called Cauchy's theorem. So you always want to look for regions. So notice it's not just at one point, it is a region. And we also said that typically a complex function being analytic everywhere is not common. So you typically will get this only in some regions, like half plane or quarter plane or so on. But this becomes very handy in physics especially. This is what we use to do many integrals. So this becomes a tool to do integrals, and that's what I want to explore. So let's say that if you have this to be, this statement is true, let us go ahead and think of another case. You simply have an analytic function, f of z, but then you divide it by z minus a. And let's say this is the same contour. So, okay, what is a contour now? So this is, let's say this is your a. It's a point A on the complex plane, and if now there is a possibility that you're actually going around the point A. So this is equal to, now we are very sure that this is equal to f of A if A is inside the domain, and it is equal to 0 otherwise. Right. So this, how do you go about doing this? It is clear that it is not analytic at z equal to a, because 1 over z minus a blows up at that point. So in that sense, it is analytic. But we can immediately see that if you have this complex plane, this is the point, and you want to go around somewhere, you're going around this point, but I can always do the following. I take a detour, go in, and then go around this point, and again come out, and then finish the contour again. And these two cancel each other. When you're going this way or that way, they cancel each other. So it is, if you were to think of this to be your region, that's analytic everywhere. So you avoided the whole region where there is where it is not analytic. So this is the same as. So let's do the following. So let's say this is C1, and that's C2. And what we can say is that C1 plus C2 of dz of f of z over z minus a, that must be 0 because of Cauchy's theorem, right? Because that's analytic everywhere. This function is not analytic only at that point, but if I make that detour and go around it, so that's actually analytic everywhere, so that's 0. Then I can split this into 2. So I have a contour integral of C1 dz f of z over z minus a is equal to, so there are 2 integrals now, so that's the same as contour integral of C2 dz of f of z times z minus a, where C2 is, and let's be slightly careful here. Now, let me draw this better because I closed this properly. So if I were to do this, notice that if I'm going counterclockwise along this main contour that I had, C1, and if I draw this in this sense, it is going down, this has to be clockwise. So there's a small ambiguity there. If I were to not draw it in that sense, then it is either clockwise or counterclockwise. So here I say this is going counter. Original contour was counterclockwise, and the inside one is actually clockwise. In general, when it is 0, it doesn't matter, but very often we will actually be talking about contours a lot. Whenever it is not clear if there is an ambiguity as to which way the contour is going, it is always counterclockwise. So in the complex analysis, whenever we talk about a contour, if there is an ambiguity, then by default it is counterclockwise. Although in this case it doesn't matter because it is 0. Either way, it is going to be 0. Anyway, so in that sense, it is C2 here should be imagined as a clockwise contour. This is different from the standard process where it is counterclockwise. So how do we analyze this? So I can make this as small as I want. So let me say there is a radius epsilon in here. So there is a small radius epsilon in there. So the contour C2 is limit epsilon tends to 0, where epsilon is the radius of this small circle that I circled around the hole. And this is, let me again write this as C2 dz f of z times z minus a. The standard substitution we will do is that we want to actually go around on a circle. So we want only one parameter that you want to integrate on. That's always convenient. So you substitute z minus a to be equal to, so you're on the circle. So you want to go around using an angle. So you keep the radius fixed. So that's the epsilon that's fixed. And it's e raised to I theta. So that's a complex number. That's your polar representation of a complex number. That's z minus a. And I keep on the contour C2, I keep epsilon fixed. So theta is what is changing. So dz would be, the a remains the same. So that's I times epsilon e raised to I theta d theta. If I make that substitution, that is how I can go from the symbolic representation of going around a contour to an algebraic way of doing it. So that's equal to limit epsilon tends to 0. Now I have to go this around. So I could have done this same displacement here also. So I can go from 0 to 2 pi. dz is I epsilon e raised to I theta d theta. Z minus a is epsilon e raised to I theta. And f of z is f of a plus epsilon e raised to I theta. Correct? The important piece in here is that this epsilon cancels out. Right? Otherwise, Like earlier, one would have thought that, oh, this diverges, but this is like you're seeing this kind of things happening in delta function also. There's a fine place when this is getting small, this is getting large, but they can cancel each other. So that's again the same thing that is happening in the limit epsilon tends to 0. This goes away. E raised to I theta also goes away. For whatever A is, unless A is 0, like you can actually say that this will always, in some limit, this will be too small compared to A. So just to put that condition very strongly here, let's say A is greater than 0. So that I can take that limit very easily. Even otherwise it works, but that you'll have to come back and work on that. That requires that f of 0 is well defined afterwards. And so that's can be taken away then. So from that point on, it is straightforward. This is equal to I times 0 to 2 pi d theta times f of A. F of A is independent of the angle theta, so that's 2 pi I times f of A. Okay. Is that clear? Like these steps that we have followed, we will be doing this again and again, and it will be crucial. There is a factor of 2 pi I that shows up here. That's because I wrote that statement wrong. This should be 2 pi I. In the main statement, there should be a 2 pi I in the front. 2 pi I times this. So that will give you f of A. Sorry about that. So right from the very beginning, there should be 2 pi I in the front. So at the end, you get a 2 pi I that cancels out, and that will give you an f of A until right. That's the major idea of a pole, like how you can encircle a pole and get a contribution from there. So this is called, if you want, you can say this is the residue of the pole. If you go around it, so we get a small thing remaining, so it's called a residue. And we will use this to work out integrals. So there will be tricks we will use. So the main idea is just this. Yes. Sure.
So let's say, 1 over z is at 0. When z is equal to 0, you have a problem, right? So if you integrated that, you would end up with 2 pi I?
No. Okay, maybe let's be careful there, okay? Yeah, good point. So that's a good example. So let's, yes and no. I think you're saying it correct, but so I think what you're trying to, so let's do an example, correct? I think, yeah, so I think what you're wanting to do is probably, this is what you're talking about, is that? So is this what you're saying?
Yeah.
This is having, okay, this is real first of all, x is real, correct? And this is going from minus infinity to plus infinity. So if you were to translate this on the complex plane, you are integrating along the real line, right? That's your contour. It's not a closed contour, right?
If you do z instead of x, like.
Okay, yeah, so let's say z, yeah, so this is, so now let us say this, you're doing z, right? Great. I'll do this, but give me, so this is now c, right? But c is not a closed contour at this point, correct? If I want to connect these two, this is not closed. But more importantly, this integral goes right on top of a divergence, right? If it is divergent, it is divergent. There is no way you can help it. Right? So that integral is not well defined. You cannot do anything about it. Okay? But since you brought this up, let's make this better. So instead, let's say we want to do x plus I delta maybe, right? And then there is slightly, because it is moved away from this point, now it is divergent somewhere here. And now you're not going on top of that, and then you're good. If you encounter, if the contour is going through the point, then there is no hope. If it is divergent, it is divergent. Like, often, how do you say this without? There are, in the literature, you will find meaning to that dx over x, but I would say in the strict sense, it is meaningless. If you don't put a delta, that's just not okay. If it is divergent, you cannot help it. Cauchy theorem cannot help you if it is not analytic at that point.
Okay.
You can, so for example, typically what you will do is, oh, this is not well defined, so let me go around that. But that's no more the same integral. And you change the integral. A small contribution can give you a large factor.
Even
And
if
in this case,
you go around it when you let that change go to 0.
yeah, and let's do that. Let's do that example, and we will show that actually the tiny going around will contribute significantly. Otherwise, it is not well defined, and if you go around it, it actually picks the residue. Right? So it's a matter of definition there, but surely you cannot say that this is the same as this. You can always say that I'm doing this and I move the pole around. So the better way to say it is that let me push the pole out, and a limit when the pole reaches, it has some meaning, but never when it is actually on top of it. You can approach the point, but never on top of it. Right? And this is done. So this is the main idea of the Green's function. I think if you have heard the word Green, yeah, we did use it somewhere else. Did we do it in UNM? Yeah, not yet. Yeah. So Green's function is a common thing used in electrodynamics, and that is how you will see this coming up. But all the careful analysis will always keep the contour the same, or the physics will actually change the pole, not the mathematics. Use the physics to begin with, not have the pole at all. So let's do this example properly. So let's say this is, I think, a good example. So let's say this is I is equal to dx over x plus I delta, and that's the integral you want to do. And is that? Yeah, so let's do that. Yeah, so let's say A, right? Let me not even say delta. Let's say A. A, only thing we say is that A is greater than 0. Or A should not be equal to 0. That is the best thing to do. It can be plus, minus or plus, but it shouldn't be 0. So for now, let me say A is greater than 0. And you would like to evaluate this. And we immediately see that now we want to switch over to the complex plane. This is real, right? You're typically working on a real line, so this is real. Integral wasn't real, but you want to switch over to the complex plane so that you can use Cauchy's theorem. And then you learn that x is on the real line. So that's your somewhere, if I were to get this part as a part of the contour, then I have a chance of using Cauchy's theorem. So first you capture that, And then you notice that, oh, this function that whatever I'm doing, if I were to take it over to the complex plane, it will have a hole here, right? So what am I doing? Saying that this is real, so that's not where that is. So so what I'm saying is that let's construct a new function, not the old function, but now this is a complex function, z over z plus IA. And I have to specify the contour now. So in this, for this complex function, there is a pole at z equal to minus IA, that's this. And now I have to make this close so that I can use Cauchy's theorem, and I can close it upstairs, going upwards or downwards. It doesn't matter. It might seem that it does matter because one way you're actually encircling the hole when you go through the bottom half, the other half it doesn't, but actually we can show that that doesn't. First, let's do this way. So that's your contour. So now it's a closed contour. So let's say this is C1, that's your C2. So that's your C1 plus C2. And yeah, I think that's all that is. Oh, but you would, at some stage, you would like to reach minus infinity to plus infinity. So let us say this has a radius r, and this is limit r tends to infinity. In the limit, this contour C1 becomes actually your integral. So again, I was interested in that integral, but judicially, I chose a complex integral instead. And this integral, I know the answer. Right? What is this equal to?
2 pi I.
Tell that again?
So now just equal to 2 pi I?
No. Because Cauchy's theorem, right? This is a contour. We ask, is this analytic in this domain? Is there anywhere you see it is not analytic?
Is there still not a hole at 0?
No, right? Because the whole, I moved it. So we are doing this.
We're just doing the second.
Yeah, we are doing this, right? That one also we are having an A there, but that's a real integral. So we'll come to that. But we are doing this. But notice the trick is to use Cauchy's theorem. We want a region of analyticity. So on the top half, it is analytic. So immediately this is 0. That's what Cauchy told us. That's 0. But how does this help with that integral? Now we break the two contours. There is a C1 and a C2. Right? This means that I have C1 dz. On the C1, it is a real line, right? dz is the same as dx. So it is dx over x plus ia. Why did I change from z to x? Because on the real line, z is x. Right? That's just a substitution if you want. And plus C2 going counterclockwise, dz over z plus ia, and I have to take the limit r tends to infinity. That's equal to 0. That's Cauchy's theorem telling us. But this is our integral. So if I can evaluate this, I get my integral. Right? This is my I of A. That's my integral I'm interested in. So I know how I can get it. Don't do it on this line. Do it on the other part. And sometimes that's easy. So that's the trick. So you do, your integral actually is getting contribution from C1. But Cauchy says that it is 0. So do it on another path and equate them. Right? This is the idea of conservative force. If you're going from here to another galaxy and you know what is the potential energy difference, gravitational potential energy, you can come by any other path, still it's going to be the same. So you can test the other path in that sense. So your integral was around the real line. Maybe you don't know how to do that, but that's equal to this. It has to be equal if Cauchy square. Clear? So let's try to do this. This is on a circular contour, so the substitution will be z equal to r. And earlier we substituted epsilon, now it's r e raised to I theta. Right? That's the substitution. And now the theta is changing, r is fixed. So dz is equal to r, so I e raised to I theta d theta, right? And so we just finished that, so that's minus, and we have to take a limit r tends to infinity. The contour is going from 0 to pi, right? That's 0 to pi. Right? If you say this is angle theta, right? It's going from 0 to pi, and dz is I times r e raised to I theta theta, and in the denominator you have z plus IA. So z is actually I could have done better, probably. No, okay, but it doesn't matter. So this is r e raised to I theta plus IA. Right? And again, we have to take the limit r tends to infinity. When I'm taking the limit r tends to infinity, it is so large that it's only this going to contribute. I can actually neglect this. Right? This goes away. So that's usually called Jordan's lemma, how you analyze that. You can actually expand this if you want, but let's do this in a very simple way, in the sense that if this is large, that is small, so this will dominate. Right? That's one way of looking at it. And when it dominates, it is r that is the coefficient that cancels that. So this is minus of limit r tends to infinity, if you want. Or let me do this in 2 steps. It's I r e raised to I theta theta. This is r e raised to I theta, and 1 plus I times a over r. I said I will not do it, but I will. So r cancels out, e raised to I theta cancels out, and this in the limit r tends to 0 with respect to 1 can be neglected. That's 0. One has to be careful when you're doing that. These are all nice functions, tested functions, so that's okay. But sometimes you want to be careful about that. So that's gone, that's 1. There's nothing in the denominator except the 1. In the numerator, there is just an I remaining. So it's minus, there is no r there, so we can forget that. So it's 0 to pi d theta. And I think that's why probably, Jordan, you were pointing out. So that's equal to minus pi I. Right? Minus because we went on the other side. Right? So it's minus pi I. I think that's what it is. Hopefully. Right? Minus. Yeah, I think that's correct. Okay. Okay, so one might say that, okay, that's, you chose it on the upper part of the complex plane. What if you go through the bottom part of the complex plane? You will get this additional hole there, and it should not depend on which part you took. So let's see how that works if you were actually to pick it on the bottom one. So let's do this again now. So this time you pick this to be your C1, and this time you go down, right? And this is now having a pole, so somehow you have to actually go and cancel that pole, right? And circle that pole, or you can use this residue theorem. Okay, so that's your C1, and this time it's C2, but notice now you're going clockwise. Right? The moment you're going clockwise, you have to be careful. Cauchy's theorem, when we say that f of a, especially when you're picking out the residue, you have to be careful that it is always counterclockwise. If you're actually just using 0, it doesn't matter. Right? If it is 0, then it is okay. But if you're using the statement where it was equal to f of a, then that assumes that that was was a counterclockwise contour. Okay, so let's do this again. But now it's a new function. There was a g earlier, so let's call that g1. Let's call this g2 now. Right? There's a new function g2 of a. This is equal to c1. That was c2, so let's call this c3 now. c1 plus c3. And since it's a different contour, it's probably a different function. Right? So no guarantee that these two are the same. Sometimes it could be, but no guarantee there. And this is dz over, let's again choose this to be z plus ia. So I'm just building a function. There is no need that this should be exactly that. This is a judicial choice, and that is a challenge usually in contour integrals. What function do you pick? Right? In this case, this is kind of straightforward. It's a straight, simple extension. Very soon we will do examples where it is not obvious how you do it. But usually that is a guiding principle. Okay. Again, this is what is this equal to now? So you would say this is C1 dz, or that's your integral itself, x plus ia, plus C3 dz over z plus ia. What is that equal to? This time it is not analytic. Right? If it is not analytic, but it has only a hole there, we actually know how to evaluate it. It is just f of a. It is 2 pi I times f of a, but there is no f, that is just 1, right? So this is 1. So this should be f of a, f of minus ia actually. But the function itself, f is identity. F is equal to 1, correct? Because there is nothing sitting there. Is that clear what I mean? Like, I can point it, but you guys don't see it. That's not
the first term where you use dx because z is equal to x, and then you have dx over z plus ia. Is that supposed to be x plus ia? I know they're the same, but
this one?
yeah.
So this should be dz over z plus ia, but it's on the real line, so I can substitute z equal to x, right? So dz is equal to dx. On the real line, I can substitute z equal to x as a real variable, correct?
Yeah, I was just asking because I guess on here it looks like you still have z plus ia instead of x.
Oh, so you're seeing it. Is that what you're saying?
Yeah.
X. Better?
Yeah.
Okay. And notice that this contour is going clockwise, so I have to switch the sign here, so it's minus. That's important there because I'm going the opposite to the standard notation. F is 1, so that's just minus 2 pi I. Good. So this is my integral, so that's again I of a is equal to minus 2 pi I, and this time I do minus of contour C3 on C3, so let me just write it as a term, dz over z plus ia. Again, substitute the same quantity, same substitution, z is equal to r e raised to I theta, dz is equal to I r e raised to I theta, theta. Do the same process again. C3 has a limit r tends to infinity. The limits now go from, I will go from here to there. I can say I'm going from 0 to minus pi. That's one way. Or you can say 2 pi to pi, either way, whatever you want to pick. So this, I say it is 0 to minus pi. Or you can say 2 pi to pi. dz is I r e raised to I theta, theta. And z plus ia is r e raised to theta plus. This time, let's just drop this in the limit r tends to infinity. It is just I times 0 to minus pi by theta. These two cancel out. And what is that? 2 pi I minus I, so that's, what is that? Minus pi, right? Which is minus pi I. So it works out, right? It has to. It should not matter which one you pick. Yeah. And I have 10 more minutes, so let me do one more example. Any questions at this stage? So the idea is, again, given an integral, construct a complex integral where this is part of the contour, not the whole contour, part of it. If it's a whole contour, then it is 0. You want to think of it as part of the contour. So let's do a more practical example, which we will probably see in electromagnetism also. And that is basically, think of a Heaviside step function. This is called Heaviside step function. Heaviside is the name of a person, a British guy. He contributed a lot, and he has the whole units named after him. Heaviside, Lawrence units, and So this is basically this one.
Can you turn the camera?
Oh, sorry. Doesn't have. Okay, thank you. Yeah. So Heaviside step function is a function. Basically, it is 1 if t is greater than 0, is 0 if t is less than 0. And often this is useful when you're talking about causality. If you want to say that past affects the present, but the future does not affect the present, and you want to put it pretty much bluntly inside an equation, that's one way of requiring that. You would say that theta minus t, that case, right? Here, future is affecting and the past is not affecting. So often for causal, for invoking causality, you would use this. So that's a straightforward function. But now we can ask, what is the Fourier transform of this? Often, when we are working in physics, it's very convenient to work in the Fourier space. And one would ask, how does a statement of causality look like in the complex domain, right? Or in the frequency space? Like a complex domain sounds very hard, but frequency domain is very common. Like if you were to type a music which is causal, how would it look like? How would this statement, this is a statement in time, how would it look like in the frequency space, right? So let's say tilde there, right? That's the Fourier transform of that. Fourier transform, remember, is minus infinity to plus infinity dt exponential of I omega t, and then put in theta of t, right? So if given any function, that's how you get the Fourier transform of that function. Fourier transform by construction allows complex components. So this could be real, but this is not guaranteed to be real because you're building it out of exponentials. It need not be. What is that equal to? So that's immediately you notice that, oh, so that's minus infinity to t, only when t is greater than 0, it contributes, right? So it has to be help here. So t has to be greater than 0. So this is the only where it contributes. Agreed? And what is that integral equal to? And you will see that, oh, exponential I omega, these are oscillatory integrals. Even at infinity, they contribute. So these are not very well defined. So these are the challenges that comes up. So now this is not well defined, and you're stuck in principle. But let's try to make sense of this. So let's say that, okay, this is not well defined, but I can maybe say that this is limit delta tends to 0. Is this exactly the same? Most probably not, but at least one can capture this to a certain extent by saying this is omega times delta. So it is like saying there is a cutoff in time, right? So there's oh, sorry, omega t. Sorry, t delta. What did I say? Yeah, this should be t. Okay, and now probably you can do this integral because now this is real. Correct? So probably you can do this integral. Can we try this? So let's see. So this is equal to limit delta tends to 0, 0 to infinity dt, and I would say e raised to t t. So this is I omega minus delta, right? So I want to keep the minus t there, and this is minus I omega plus delta. I think that's what it is. And remember, exponentially decaying function gets a contribution in here. So the goal is that this actually dominates at large t. So this is equal to exponential minus t minus I omega plus delta over minus I omega plus delta. And this has to be evaluated at t equal to 0 and t equal to infinity. At t equal to infinity, it doesn't contribute because this exponential will kill it. So it's, the upper limit doesn't contribute, and the bottom limit is minus, and when t is equal to 0, that's 1. That's minus I omega plus delta. That's the same as 1 over I times 1 over omega, and how I pulled a minus I, so it's plus I delta. Right. Very similar to the function that we already dealt with, but that's not what it is. There is a 1 over, so this is how your Fourier transform looks like of a simple function like 0 to 1. How do you interpret that? That's no intuition there, right? But let's at least verify, right? We won't finish it, but let's at least verify next time. So if I substitute it back, right, theta of t is also equal to, like this is the inverse Fourier transform, minus infinity to plus infinity d omega over 2 pi times exponential minus I omega t times theta tilde of omega. That's the inverse Fourier transform. If this is known, then we should be able to verify that e raised to minus I omega t, and that is 1 over I is 1 over omega plus I delta. So let me rewrite this as 1 over 2 pi I times minus infinity to plus infinity d omega It's very similar to the example we already did, except that now there is an exponential. Right? Most of the things remain the same. We choose the same contour going this way or that way, and we will be able to show that in one case, this will be equal to 1, and the other case, it will be equal to 0. We'll postpone that to next time. Did I give an extra credit problem today? You did not. I did not.
Although our digression at the beginning would serve as a.
Yeah, why don't you give an example? Yeah, what was the?
So I have one question about what you did really quick too.
Uh-huh.
When you pulled out the negative I, oh, never mind, I got it. It's negative I. So when you pull out the negative I, you have 1 over I, then you have a minus sign for the delta, and then your delta divided by I, which is equal to, okay, that's why it's a plus. Okay.
Yeah, I think it's okay. Yeah. This plays an important role in what is called Kramer's chronic relation in electromagnetism. We will encounter this again in our electromagnetism, where we will actually use it for physical example. Here it is just next slide. So, yeah, how about extra credit? Just state Kramer's chronic relation. You won't see this exactly this way, but you will see the structures in there because you begin with that. So that's the extra credit is to just look up Kramer's chronic relation. It's called relation.
I still have a question about the sign.
Oh, here, did I make a mistake?
So when you integrate the e to the minus t minus I omega plus delta, do you need another negative in that antiderivative?
Oh, because of this negative sign here? Yeah. Probably.
Yeah.
That's correct. Because this is the coefficient there. Probably that's what Jordan was also trying to point out. Right? So this is minus, yes. Right? Minus of this because that's a coefficient there, right? That's correct. So minus, and then this becomes a plus, and then I pull out a minus I. So this is a minus I pull out. So that's minus I then. Yeah, okay. So that's minus I. So this is minus I. I think that's correct. Yes, that is correct. I have it written down here. Yeah, that's correct. There is a minus sign there. This minus sign should be there in this. Yeah, good catch. You could attempt this to show that this is actually 1 and 0, but I will do that in the next class. And extra credit is just Kramer's chronic. But yeah, good questions, good thoughts. Good catch. Thank you. Here is the class that is Moses.
So getting married, huh? Congratulations.
And then
Thank
again,
you.
Wow. Yeah, congrats.
Thank you.
Everyone's getting married.
Yep, I'm getting married
Yes.
this month.
yeah.
Wow.
So if so, Michael was saying that he wanted to take the exam while he was getting married. That was his suggestion. So I thought we will excuse him with the exam. I thought that was reasonable.
Yeah, for sure.
What's the date?
October 24th.
Okay.
Since we are excusing you with the exam, you should invite all of us.
Right? That'd actually be pretty interesting.
We can have an exam in your reception or something.
Right.
That'd be fun.
Good,
Where are you
congratulations.
getting married at again? You said it was far away.
Yeah, Weston, Missouri.
Where is that exactly?
It's just north of Kansas City.
Okay. Like St. Joseph area or?
I think so. It's right across the border from Leavenworth.
Okay. I know what you're talking about. Ish.
Right.
Everything in northern Missouri is ish.
Yeah, exactly.
Most of Missouri besides Kansas City or Columbia or St. Louis, obviously.
Mhm.
Fall weddings, they're cold.
Yeah, I didn't realize it would be that chilly already. But yeah,
Yeah.
she wanted a fall wedding, so
Yep. Well, I had mine in the summer, and we did ours outside too. It was so hot. I think fall might be better. We were just like sweating, and it was miserable.
yeah, that'd be a nightmare.
But our ceremony was only like 1:30, so it didn't take too long. It took her longer to walk from the building to where we were getting married than it did for our ceremony. So it's pretty quick.
Yeah, my sister got married in January in Minneapolis, so that was a pretty cold wedding.
Oh,
I bet. I
Yeah.
bet. I bet. My brother, he married a lady from Denmark, and so she went to school here. She had her master's degree here, and she was living here for like 4 years and applying to get her green card. And for those of you who don't know, it's not so easy to get. And so her and my brother were going to get married. And in order for her to be able to stay in the States for a wedding, they had to get married before they officially got married. Like their official marriage happened before the ceremony. So they got married like 3 months before their actual wedding. So they had that wedding with a small gathering of like close family. And then they had a wedding in the United States. And then they had a wedding in Denmark for her side of the family. So they had 3 weddings within like a month and a half from each other. So by the time that was over, everybody was like super weddinged out. And then 2 months later, I got married. So it was a lot of weddings. But in Denmark, it was like May-ish, but it was very cold in Denmark in May. Surprised.
Well,
I'd
I
be
gotta
surprised
go,
if anybody
congrats.
showed up to your wedding. Yep, see you later, Luke.
Dude,
See you guys.
Good.
alrighty. Well, congrats.
Thank you.
Yeah, enjoy.
What happens once for most of us. So enjoy it. See you guys.
Thank you. See you guys later.
Yeah.
Bye.
Bye.